Hi guys, welcome back. Hope you all are doing really good. And today we are going to continue working on some more logic problems. We're going to learn a little bit more about how to use truth tables to evaluate pairs of sentences this time. So thanks for being here. And we'll all be getting started in 8 minutes or so. Be right back, guys. Just a few more minutes till it's 11:30, so welcome everyone. Hey, Brenna. Nice to see you. Hey, Jamie. Hi, Rachel. Welcome, everyone. Hey there, Arlene. Yeah, I did send it just now, Brenna, just a moment ago, right before the class. So the announcement may not have posted to your email yet, but it's in the queue under our announcements tab in the Titanium page. So yes, it's there. Hey, Ethan and Yvette. Yeah, no problem. Thank you. Hey, Leo. Hi, Nathaniel. Good to see everybody there. Good morning, Natalie, and all the rest. Hi, Samir, Valeria, everybody here. Welcome back. Hi, Jasmine. Hey, Stephanie. Good to see you too. Marissa. Hey, Kimberly. Okay, just another minute, and then we're pretty much good to go. Hello, hello. Hi, guys. Anna, Amaya, Johnny Red. It's good to see you guys here. Hello, Isaiah, Josephine. Always nice to check in with you guys. Hey, Ella. All right then, so welcome back everybody. I'm glad to see you guys are here, and it's 11:30, so I'm just gonna get us started. Okay, so a couple of things. I wanted to take a moment, even though I've sent the answer key to everybody for homework 1 with explanations for the correct answers. I kind of wanted to go over it just briefly here in the meeting, some of the topics on that homework problem set. To just totally clarify, any misunderstandings that there might have been, because many people could have done a little bit better on this, and some of the mistakes were just kind of fundamental things at the beginning. The first 5 questions, it seems like people are still thrown by the whole concept of what is a valid argument. So I want to make sure that we don't, have any confusion on that. So let's see here. What I'll do is I'm looking at the homework problem set here, and I'm just going to go over some of the questions. So question 1 says this: if all the premises of an argument are true, the argument is valid. Now, question: is this a true or a false statement? What you see written there. Is it true or false that any situation where the premises are all true automatically means that it's a valid argument? Okay, it's false. Correct, it's false. So why is it false? A lot of people said true in the homework, but it's absolutely not true. You can have an argument where all the premises are true and it is invalid, and that's obvious because An invalid argument is one where all the premises are capable of being true and the conclusion false. If you just look down into a couple problems later, question 6, it says, provide this argument, an invalid argument, all of whose premises are true and whose conclusion is false. So just having a bunch of true premises does not guarantee validity. If the premises are all true, but they have a conclusion below them that does not follow from those true statements, then it would be an invalid argument. Like, so if I told you, for example, look at this argument, Vulich is a professor, therefore the world will explode. That's not valid, okay? But the premises, they're all true, because yes, I am a professor. So we have to understand that validity has to do with whether or not the premises logically support the conclusion. If they support it in a logical way, then it would be valid. But if the conclusion is not proven or generated by the premises, then it's an invalid argument, no matter whether the premises are true or false. Okay, so you can have invalid arguments where all the premises are true, like for example here. That's why this is not the case. If all the premises are true, the argument is valid? No, not necessarily. Okay. Well, let's go ahead then and look at the next one in this list. The second question says all valid arguments are sound. Is that true or is that false, that all valid arguments are sound? That's the question right now. All valid arguments are sound, yes or no? Is that true or false? Okay, correct, it's false. It's false. You can have valid arguments that are not sound. If the premises imply the conclusion, that's all it means for it to be valid. But, of course, you can have arguments that are valid where some of the premises are not real facts. So, take this example. All dogs are purple. Terrier is a dog. Terriers are dogs. And then what would be the conclusion of that argument? All dogs are purple. Terriers are dogs. Therefore, thus, hence, so, it follows that, consequently, ergo, what's the conclusion? All terriers are purple. Okay, question. Is that argument valid? Yes. Is this argument sound? No. So the statement that all valid arguments are sound is not a correct statement. There are valid arguments which are not sound. If all valid arguments were sound, then you would not be able to provide an example of one that was valid and not sound. But here is one example like that, and there's so many more that you could possibly give. So just know that soundness is validity plus. It's validity plus having true premises. But validity does not depend on the premises being true. No. Okay. So the next question, number 3, it said, sorry, I'm just going to pull it up here. 3 says, every argument with a true conclusion is valid. Now, is that a true or a false statement? Every argument with a true conclusion is valid. Little edit. Yeah, every argument with a true conclusion is valid. Is that correct or not? What do you think? If it's got a true conclusion, is that all it takes for it to be valid? Okay. Really, Arlene? A couple of us are giving that information. Where's the rest of you guys? Okay, see a few more. Now, yeah, this is false. This statement is false. What the statement says is that every single argument with a true conclusion is valid. Now, why is it false? Somebody tell me why that is false. Why is it false? Okay, so Stephanie, it is correct that if the conclusion is logically true, then the argument is valid. But that's not what's being asked here. This question has nothing to do with logical truth. It's just truth. So the question says, every argument with a true conclusion is valid. Right, the conclusion might not follow from the premises. In that case, the argument is invalid. Now, some people, when they gave the answer that it's false, but they gave the wrong reason. That's something that I noticed a lot of cases of. People would say, for example, something like, even if the conclusion is false, it can still be valid or something like that. But the example that you have to give to show why this is false is to produce an example of an argument with a true conclusion that is not valid. When there's an argument with a true conclusion that's not valid, that shows us that just having a true conclusion does not necessarily mean that it's valid. So working backwards from this conclusion, Trump is the president, is true. But if I just have, I don't know, let me think of something totally unrelated. This is not about the special case of validity. No, Jessica, this is not about that. So Trump is president, let that be the conclusion. What's an invalid form of reasoning to lead to that conclusion? Maybe the premise that, I don't know, Trump is from New York. Is that a valid argument? No, it is not a valid argument. Yes, you will submit the homework, Leo, the same way as last time by email attachment to me. Just you'll send it to my email account. And you know that it's in the syllabus. But this argument's not valid. The conclusion is true, but the premise does not imply the conclusion. Why is that an invalid argument? Because it is theoretically possible for the premise to be true and the conclusion to be false. Obviously, just being from New York doesn't guarantee that a person who's born there is president. Otherwise, every citizen from New York would be president. You understand? So this is a true fact, but this is not a reason that implies this. So this is invalid. Since you can have invalid arguments where the conclusion is true, this statement is false. Every argument with a true conclusion is not valid necessarily. Okay? Now, the fourth question just said, true or false. If all the premises are true and the conclusion is false, then the argument is invalid. And that's true. If the premises are all true and the conclusion is false, it cannot be a valid argument. You know already in that situation that it is invalid. Because valid arguments never show that combination of having all premises true and the conclusion false. Okay, so valid arguments can have, like any other possible combination, some combination of true and false premises with a false conclusion or a true conclusion, or all the premises in conclusion are false, or they're all true. But it will never be valid if all premises are true and the conclusion false. That contradicts the definition of validity, which is that in a valid argument, it is impossible for all the premises to be true and the conclusion false. So most people got that one. But then, question 5, a valid argument with at least one false premise and a true conclusion. All right, so that is just like giving a valid argument where one piece of information in the premises are false. Like if I say that all men are 7 feet tall, so wait, the instruction says that it's got to have at least one false premise and a true conclusion. So how about this? All men are short. Kevin Hart is a man. Therefore, Kevin Hart is short. You guys know who Kevin Hart is, the comedian? So if you know who he is, maybe you'll catch this reference. He's a short man, he's short. Okay, so this is true. This argument is valid because these two premises logically imply this conclusion. But, okay, are both of the premises true? No, because not all men are short. We've got tall people all around. Shaquille O'Neal, you know, Kareem Abdul-Jabbar, a lot of basketball players that are tall and other people too. So it's a valid argument, but you have one false premise and a true conclusion. So something along those lines is all that you need to get the right answer for 5. A valid argument generator where there's a false conclusion is easy enough to give. Just make an all statement where the all statement is false. All men are tall, all men are short, all girls have short hair, all girls have long hair, you know, and on and on. If you say that and that's false, you can still follow the logic through to some conclusion based on that premise, okay? Now, number 6, an invalid argument, all of whose premises are true and whose conclusion is false. That one was like so easy because if you just follow the directions, the premises are facts, the conclusion is false, it by definition will be invalid. So that one's easy. The next one though, something that I noticed with a lot of the wrong answers where people didn't follow the direction of making the argument actually invalid. So like a lot of people with number 7, what it says is give an invalid argument with at least one false premise and a false conclusion. Many people provided an argument that did have a false premise and a false conclusion, but it was valid, you know? So like people will say, all dogs can fly, terrier is a dog, so a terrier can fly. But the problem with that example is that it doesn't fit the instruction. The instruction says that it has to be something invalid, where the conclusion does not logically follow from the premises. So you have to make sure that the conclusion is unrelated or not implied by the statements of the premises. Okay, now number 8. I was kind of interested to see that many people got number 8 wrong, where it says give a consistent set of sentences where there's at least one true member and one false member. Some people said that's not possible. If they're consistent, they have to have the same truth value. No, no, no. That's not what consistency means. Maybe you're thinking of equivalence. If they're equivalent, they have to always have the same truth value. But consistency just means that they could both be true in at least one possible situation, not that they actually are both true in the real world. So who could just give me a quick example? 2 sentences, one of them's true, one of them's false, but looking at them as a set, they are consistent. Who can put one of those in the chat? Let's see. 2 sentences, there's one that's true, there's one that is not true, but they could both be true in a different possible world. That's what you have to give. So let's see what you've got. Many people got it right, but then there were some that got confused. We are in a pandemic and Hillary Clinton is president. Okay, good. So is there a possible world where Hillary won in 2016 and we still had to deal with this coronavirus problem? Yeah, that could have happened. It's not what actually happened, but it's not impossible that it could have. So those 2 statements don't contradict. Therefore, they are consistent with each other, although one is true and one is false. Leo, Kobe Bryant is alive and Hillary Clinton is not president. Okay, good. Yeah, so, well, wait, no, wrong, Leo. The example says one true and one false, but both of the things you say are false. Or, sorry, wait, no, she is not president. Oops, my bad. I didn't read it right. Thank you. So it's true. Hillary Clinton's not the president. That's true, but Kobe Bryant is alive. That's false. Nonetheless, those 2 things could have been true. Correct. Thank you, Leo. It could have been that Kobe didn't get in the helicopter crash, and, you know, in that situation, still it's Trump that's president or not Hillary anyway. Okay, good. So then let's look at the number 9. A consistent set, all of whose members are false. So it's just kind of the same thing we just did where there's one true and one false, except now make them both be false, but not contradictory to each other. Let's see, who can throw out any pair of statements that are both false, but that are still consistent? What do you think? They're false and false, but not contradictory to each other. Okay, Ruby, so I see people like the example of Kobe. You know, it is sad that he is gone. But anyway, let's think about that. So Ruby, Kobe's alive. No, he's not. We're not in a pandemic. Yes, we are. So those are 2 false statements, correct. But they could easily both have been true in a different possible world. Right. Okay, fair enough. Good example. Anybody else? Want to throw one more out there? How about something that breaks the mold, guys? Let's stop with all the who's president, whether it's a pandemic, and whether it's Kobe being alive or dead. Just come up with something of your own you've never heard before. How about that? 2 false statements that are consistent. To be able to just generate these at will. Let's see it. We wait for it. Two things that are false, but not inconsistent. So I don't want you to over-rely on just a couple of examples that have been mentioned in this class. LeBron James has won a Grammy and a triangle has 6 sides. Well, sorry to say no, Brenna, because your second sentence is logically false, which means it can never be true. And if it can never be true, then it can't be true when the other one's also true. You know what I'm saying? So it's not correct. Ethan, McDonald's is not a worldwide chain, and Will Smith was never famous. Okay, that's creative. I like what you've done there. So both of those things are false. McDonald's is a worldwide chain, and Will Smith is world famous. But imagine a world in which McDonald's never became a big restaurant and it's just a couple of little franchises. And in the same possible world, Will Smith, I don't know, he never got his starring turn on Fresh Prince or something. So anyway, you can imagine those two things had been true in some situation, but not in our actual situation. So they're consistent, but they're both false. LeBron James has won a Grammy, Brenna, and Dr. Vulich has won a Grammy. Okay, neither of us have won a Grammy, but I guess if the world had turned out a different way, maybe those two things could have happened. They're certainly not in conflict with each other. So good example. Okay, so looking at the next. Logically true sentence. Now let's be clear about that. Logically true sentence is not like the Earth is round, okay? Because the Earth and its shape, I guess if physics had taken a way different track, maybe it could have been a different shape. I mean, so it can't be something that's like obviously true, like Donald Trump's the president. That's not logically true because it could have been false if events had occurred differently. So you got to go with math. You got to go with geometry. You got to go with just pure logic. You could have said like the brown dog is brown, you know, saying anything of the form A equals A, that's logically true. But the easiest supply of these examples is just math. 2 + 2 is 4. There's 4 sides on a rectangle and stuff like that. But anything else that's a matter of probability, even if you think it's a given, it's not logically true, okay? And then about logical falsehood. Many people gave bad examples of that too. People saying things like, the Earth is flat, that's logically false. Or, I don't know, there's a lot of examples of things that are not like a false mathematical statement or an incorrect geometric statement. So for it to be logically false, it has to have like 0 possibility of being true in any conceivable scenario. So it has to be like 1 + 1 is 10, or, you know, dividing 5 by 2, sorry, 10 by 2 equals 20 or something like that. Okay. So then we get to the logically indeterminate sentences. And that, I think, is easy enough because that's just anything that's a matter of fact that could have played out different. So what's hit me with a random logically indeterminate sentence? Who can think of one really fast? I just want to brush past these, you know, I want to review it in the lecture with you guys one time, this first homework assignment, so that everyone's clear. But something logically indeterminate could be like what? Just one sentence, not a pair, or not a set. On May 1st in such and such year, an earthquake occurred in what is now Southern California. Okay, good. Now I see, Kimberly, that you're really leaning heavily on an example from our textbook, which gave an example like that. Or it's raining, or it's snowing. Okay, good. Something about the weather. Those are all good examples. How about something that has nothing to do with weather at all? Give me another one. I'm wearing a hat? Okay, good. I don't know if you are or not, but whether you are or not, that's still logically indeterminate. It's something that could be true or it could be false. That's why it's indeterminate. It's not that it has to be true. It's not that it has to be false. It's one or the other, and it's possible to be either one. Your favorite color is red. Okay, good. If it is red, that's a great color, but I guess your tastes could have developed differently, and therefore that's not logically true. The Lakers are in the NBA Finals. Do you guys know that? The Lakers are in the NBA Finals, but that's just logically indeterminate because obviously it could have gone any number of different ways that they did not make the finals. So that's not like 1 + 1 is 2, which has to be true. It's something that's true, but it could have been different. Okay. Now, next up, a pair of sentences that are not equivalent but that are both true. I noticed many people got confused with this question. Like some said, you can't give an example. Yes, you can. Definitely you can give an example. So two statements that are not equal but both true. Let's put a few of them out there. There's already a bunch of them here in the chat, but let's get a new case. Two sentences that are not equivalent, nonetheless they are both true. What could be an example like that? Both true, two true things, but that don't have logical equivalence. So let's see. You're a student and you're a girl. Okay, Lily, good. You are a student and that's true. And you're a girl, that's true too. But although those two things are both true, they're also not equivalent. It's not the same thing to say that you're a student as to say that you're a girl. For example, there could be a situation in which you're still a girl, but you're not a student. Like if you drop out of college tomorrow, then the one thing will be true and the other will be false. So they're not equivalent because they can vary their truth values. They can diverge. One can be true while the other one's not. Since that's even possible, they're not equivalent. Equivalence means you cannot even dream of a situation where they have different truth values. So if you can imagine a situation where they don't have the same truth value, they're non-equivalent. But whether they're both true or false depends on this world and what's going on in it. Ethan, fish swim in the water, basketball players play basketball. Okay, so I guess thinking of your example, it's possible for there to be a world where basketball players play basketball, but fish, I don't know, are somehow elevated to the land. Maybe they've evolved some manner of breathing or locomotion that enables them to move terrestrially like a mud skipper or something. So look, if evolution had taken a far different track, then I guess the fish that we think of as being water animals could have been somehow terrestrial. And in that situation, we could still have people playing basketball, or the other way. But Ethan, your example is a little weird to be fair, because when you say basketball players play basketball, it's hard to even imagine a situation where that's false, because it kind of sounds like teachers teach, which is definitional and therefore logically true. So it's hard for me to give the case where basketball players don't play basketball, but still fish swim in the water. You understand? But I'm taking what you give, and it's still a valid example. Okay, so the Lakers are in the NBA Finals, and you're a student at Cal State Fullerton. Those are two things that are true, but there's certainly possibilities where they're not both true, and only one is and not the other. Anything like that is the kind of answer you want for question 13. Now next up, 14. A pair of sentences that are logically equivalent, they are equivalent, but they're both false. Okay, so now I want you to think of two statements that are not facts, that are false, but they are equal logically. So what are two such statements? Let's see one example given here in the meeting. So two statements, they're equal logically, but they're false. So what can you say? Two false but equivalent sentences. So I'm just hanging in there and waiting for your typed response in this chat. Evelyn, CSUF only has 10 students, okay? And 10 students attend CSUF. Those two statements are logically equivalent, correct? And they are both false. So exactly, that's a good example. Now, Brenda, another good example, except your example is of logically false things, but it's true. Any two logically false sentences are equivalent because both of them can never be true, so they always have the same value of f. And yeah, rectangle has 3 sides, false. Triangle has 6 sides, also false. So those two things are false, but they're also logically equivalent because there's never a case where one is true and the other is false because both of them can't be true. Okay, drawn red. Dwayne Johnson is shorter than Kevin Hart. Good and interesting example. And Kevin Hart is taller than Dwayne Johnson. Yeah, so you guys know about the sort of silly relationship of The Rock, Dwayne Johnson, and Kevin Hart, that short comedian guy. So anyway, yeah, Dwayne Johnson's obviously much taller than Kevin Hart. So saying it in reverse is false. Dwayne Johnson is shorter than Kevin Hart is false, but that's logically equivalent to the statement that Kevin Hart is taller than Dwayne Johnson. Okay, good. Now here's a point I wanted to make quickly. When you're asked to give an example of a statement that is either false or true, you have to make sure that you don't just invent made-up characters. Like I saw some people being like, Bill loves Ted, or Bill is Ted's neighbor and Ted is Bill's neighbor. But Bill and Ted, I don't know who you're talking about. You're probably talking about the film characters, but that's not real people. So you have to give real facts. You have to give like real names of actual people who I know, so that I can determine whether your example is one that's true or false, because the world is the thing in which the statements are either true or false. So you can't just be acting like you're writing a little novel, like, okay, you know, Jack and Jill went up the hill or something. It's not a real situation. So truth and falsity involve reality. Okay, next up, with 15, two sentences that are equivalent, but one's logically false and one's logically true. That's just not possible. So that's the one where you can't give any example. Because if one statement is logically true, then it can't be false. If one statement's logically false, then it can't be true. So in that case, they will never coincide in their truth value, and two equivalent sentences have to always coincide in their truth value. 16 and 17. Okay, so this was the little part of the homework which talked about whether the set of sentences written down is consistent or not. And I was kind of, most people got it, but I was so surprised in a way that some people didn't see that just these are inconsistent. 16, what does it say? Henry likes real ice cream. Real ice cream is a dairy product. And the third one says there is not a dairy product that Henry likes. Now, I'm not sure how anybody thought those are consistent. I mean, it says right there, he likes ice cream. We know ice cream's got dairy. And then the other statement says he does not like anything dairy. So those cannot all be true. They can't all be true, because if he does like dairy, then it's not really the case that there's no dairy product that he likes. But if it's true that there's no dairy product that he likes, then it would be false that he likes ice cream, because it is made of dairy. So these three statements cannot all simultaneously be true. And then the next one. Sue is taller than Tom. Tom is taller than Henry. Henry is just as tall as Sue. Fewer people made an error on this, maybe because they were just thinking about height. And yeah, it's not possible, because what it claims is that Sue and Henry are the same height, but at the same time it says Sue is taller than Tom. How could she be the same height as Henry if she's taller than Tom? Because Tom himself is taller than Henry is. So these three statements cannot all be true. Another thing about when you evaluate the statements to see if the set is consistent or not, I noticed that many people kind of, the way they said it is like that these are facts. They're like, he likes ice cream. So he shouldn't like, so it shouldn't be true that he doesn't like any dairy product. But nobody's saying that any of these are factually true. We're just saying that if they were, they would contradict the other ones. That'll be clear also, I think, in, like, let's look at number 18. So 18, Henry is in love with Sue, Sue is in love with Henry. Are those two sentences equivalent, or are they not equivalent? What do you think? To say that Sue loves Henry and Henry loves Sue, are those equivalent, yes or no? A loves B, B loves A back. Is that equivalent? No. Okay, good. And why not? It is because it's possible for the one to love the other and not for the other to love the one. Now, many people said it like, we don't know if Sue loves Henry. I thought that was funny. It's like everyone's thought process was, we know Henry loves Sue. We just aren't sure if she loves him back. You don't know whether either of the statements are true. So it could be that Sue loves Henry and Henry doesn't love Sue. It's just that it's possible for one to have that fact and not the other. Since that's possible at all, the two statements are not equivalent. Okay. Sue married Barbara, Barbara married Sue. Number 19. Those are equivalent. Because with marriage, you can't marry a person asymmetrically. It's not possible to marry another person that does not marry you also. Unlike love. I can love people that hate me, but I can't marry people that don't marry me. So the statement that they're married is either both true or both false. If one's married, then so is the other two then. But if they're not, then the other isn't either. So they have to have the same truth value. And then finally, the last one is also not equivalent. It says, I know there are people who are starving in every large city in America. And then the second sentence is, in every large city in America, I know people who are starving. That's different because one says that you know the general information that there are starving people in each big city. The second one claims, though, something more specific, that you know the people that are in the cities. So you probably don't know such people, even though you know the basic fact that there are such people. So those are not equivalent. Okay, so that's just my little helping summary of the first homework. I did provide the answer key, but I wanted to kind of emphasize the correct answers and give it a record on video here that you'll be able to refer to later if you need it. So moving on from that, we still have to develop a little bit more on these truth tables, okay? So I'm going to just take us right back into the whole truth table material. Let us look at some of the examples that are written here in the book. Maybe right now, what I'd like to do is pull up some of the examples in a Zoom format. So let me give you guys a link, and then we can switch over to that. Okay, I'm about to put it here in this chat. So there I'm dropping the link. Go ahead then, and by clicking the link, you'll join the meeting in Zoom. Then I can just display on the screen some of the practice problems that I want us to look at for a moment. So let's go. Okay, guys, here we are. Let me share the screen. Okay. So hopefully you can see what we're looking at here. I want us to take a quick look at some of the problems here in section 3.2. Okay, so what I'm looking at is this little section here, section 3.21, A through L. Okay, and as you can see, here's the instruction. Construct a full truth table for each of the following sentences of SL and state whether the sentence is logically true, logically false, or logically indeterminate. I prefer the terminology logically rather than truth functionally. This is a synonym for that because logically is just one word, and it's, I think, less of a mouthful than the term truth functionally. But just understand that that's the interchangeable label for logically true. Okay, so let's go ahead and try and do a couple of these. After we've done that, I want to talk to you guys about how to use truth tables to evaluate pairs of sentences and to see whether they're equivalent using the truth table method. But let's remind ourselves and refresh our memory about how to do these really quick. So I'm looking at question D for the moment, all right? Question D right there. So this is problem 3.21D. So the problem is to create a truth table for this formula and then to just see what status the sentence has. Is it logically true, logically false, or indeterminate? So to the top right of the truth table, we put the sentence that's going to be analyzed. And there it is written as to the right of letter D. So it says that if E, if and only if H, I'll use the double arrow. So if this biconditional, then in that case, this regular conditional, which says if not E, then not H. Okay, so that is the formula. Now, question to get the truth table filled in. What's the main connective of that big formula? Who can tell me? Oh, sorry, let me get the chat up to pop up really fast. Here we go. Okay, here you see our chat. And so anyone just let me know in the chat. It's the first arrow, the single arrow here, the one that groups the two parenthetical expressions. Correct, guys. So this is where we will draw a downward facing arrow to designate that that's the main connective. Now, up here on the top left, that's the next step. We have to list the letters in the formula in alphabetic order, left to right. So how does that go, and what's written up here? Just let me know. EH, correct, L. Okay, so here's E and H. Now, the next thing to question is how many rows will be needed in the truth table? How many horizontal rows? 4, exactly. Since there are 2 letters in the overall formula, it necessitates a total of 4 horizontal rows. Underneath E, we'll draw T's and F's going down in a 4-item list. So how will the display vertically look underneath E, starting at the top and going down to the bottom? 4 items, T, T, F, F. Correct. So then underneath H, we also have to create TF, TF. That's correct. Now, we simply are going to assign these truth values to the letters E and H in every single horizontal row. So in the first row, E and H are both true, and so T is placed underneath them in the corresponding position of the table. In the second row, E is true and H is false. So we show that by means of this assignment of letters. In the third row, E is false and H is true. So under each case of E, there's an F written, and under each case of H, there's a T. And then finally, in the fourth and final row, both of them are assigned the value F. So that's F, 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 F. Okay. So then, next, we just have to hold this for the last, because it's the main connective. That's saved for the last. Next, we're going to have to place the truth values underneath this connective, and also to fill in everything underneath the right-hand side. Since this one's a little less complicated, let's do the left side first. Okay, so based on what we know concerning the rule for biconditionals, what's the truth value in this first row? The letter that I will write in between these two. What is put here? Good, Brenna, Lily, and the rest, it is T. Why is that? Because with double arrow, with the biconditional symbol, the two things on the left and right must match in order for it to receive the letter T. And if there's a mismatch on the left and right, then it gets F. So tell me here quickly, what's this one? The second row, F. And then the third row, also F. Finally, in the fourth and final row on the bottom, we see T, exactly. And I noticed, thank you for that actually there, Isaiah. Maybe look to disambiguate which response you're answering for. You can simply write row for colon or row whatever, colon, and then I'll know. So anyway, yeah, this one's true because you have a matching set of Fs. And this one's true because you have a matching set of Ts. But in the other two cases, they don't match, so that's where there's an F. Okay, so now let us move over to the right side. This left part's all complete. On the right, we have to first assign values to the negation signs because this arrow cannot be assigned until we have something on its left and its right, which for now are blank. So let's look at the tilde symbol here to the left of this row or column. What's the letter to be placed here in the first row? Row 1, F, yes, because it reverses the value given to the letter on its right. So next case, row 2. Am I seeing the answer? Row 2 is also F. Is that what you intended to show? Just write the row number in preface of your answer. Okay, now in row 3, the, yes, value is T. And then in the fourth and final row, we see that it is, yeah, thank you, also true. So a little bit more work. We also now have to do the tilde sign to the left of H, okay? And what is in row 1 under that tilde sign? Row 1, under the rightmost tilde, we see what? Row 1, F, correct. Why so? Because it's attached to this H, which is net assignment true. Row 2, also true, good. Row 3, F. And row 4, T. Okay, good. So just 2 more columns to fill. We're now going to do this arrow here. Now, to fill underneath the conditional arrow, we're going to be looking at what's left under the left tilde and what's under the right tilde. So this is F antecedent, F consequent. That generates what here? Row 1, T. Correct. Because, Lily, as you know, the rule for the conditional is that it's true all the time, unless you have a TF left-right combination. So now move to the second row. What's written underneath the arrow of row 2? Row 2 gets the value of what letter? You have 2 options, T or F. Row 2. Okay, Jamie, how would you know where to look to get the T or the F? Oh, sorry, I saw. Okay, anyway, yeah. Where would you look? You're looking at the antecedent and the consequent that are flanking this arrow. Now, the antecedent of the arrow is not just the letter E, because this is not merely E. This is a statement that not E. So that means that you have to evaluate what's under the tilde and what's under this tilde. If they were just regular sentence letters with no connective attached to them, then it would just be the letter that you look at underneath E and H. But since these are negations, the negation is the main connective of this little formula. So you're going to use tilde and tilde on the left and the right. In general, every time you're trying to assign a value underneath an arrow in a truth table, there's going to be something to look at on the left of the arrow and something to look at on the right of the arrow. The left term may be a connective, if that is a complex antecedent, or it may be a single sentence letter if there's no complexity to it. Okay, thank you. So, by the way, you gave me the answer, Lily, that the second row should have T here, because F leading to T is not T leading to F, in which case there would be a false conditional. Now here in the third row, row 3, everyone, you see that? Good. I'm glad that you can see that that's the case where it is false, because we have this T and on the right F. That's the one case in which a conditional is false. Finally, fourth row, row 4, T. Good. Now we're almost done with the full table, but we have to fill in the last column, which is underneath that main connective, and we know that where the arrow is, that's where we go last. So with everything else filled in, what 2 parts of the left and right formula are used to designate this assigned value? We're looking at what on the left? The letter that is written underneath what letter or symbol? So to the left of this arrow, where should our eye be focused to determine what the antecedent truth value is? Yes, correct, Lily. What's written underneath the double arrow sign? And on the right side, what is the truth value to be examining in assigning a value? Right, underneath the arrow. So we're looking at these 2 parts in each respective row. And that will give us the value here. So in row 1, what is placed underneath the arrow? Row 1, let me know. Row 1, true, exactly. Because T leading to T is a case where it's true. Row 2, F leading to T. Row 2, you can let me know, is what? For row 2, yes, once again, it's a case of a true conditional, because F T is still not the only combination that makes it false. Third row, F on the left, F on the right. When it's an arrow, that yields what truth value? Row 3. Row 3, good, true. Because once again, the only combination that leads to an F when there is a conditional is if you have T going to F. But anyway, What's the fourth row finally? T combined with T on the right gives us what value in the fourth row? T, exactly. So now having completed the truth table, right, we're going to circle this column underneath the main connective. This circled column has a display, and it shows us what this sentence is. So is this logically true, logically false, or indeterminate? And good. You're getting the right answer. It's logically true. Why is that? Because these all say T. When the things underneath the arrow are all T's exclusively, that's a logically true sentence. When they're all F's, it's a logically false sentence. And when they're a combination of T's and F's, that's when it's a logically indeterminate sentence. So quickly, I can pull up the answer key for this. And it's question D. Okay. Here you see it. This everyone can clearly see. The same table that we have here on the whiteboard is in a typed form here in our answer key from the textbook editors. So just you see here the same information that we've taught. That's a logically true statement. It's demonstrated by a full complete truth table which shows only T's underneath that. In this case, horseshoe symbol, which is interchangeable with the arrow. Okay? Now, we could continue to do more and more complex formulas. Let's take a look quickly at F. I'm not going to write it all on the board, but just briefly, I'll show you the display here in the answer key. And this is compared with the question written here, F, which is quite complex. So what it says is that both, and then there's this huge crazy conjunction, both C and both if C then D and if D then E and not E. So that's three sentence letters. The alphabetic order is C, D, E, okay, which generates 8 rows in that case. Now when you have 8 rows, because there's 2, 4, 8, after you go 3 to the power of 2, no, sorry, thank you, 2 to the power of 3. So 2 to the power of 3 goes 2, 4, 8. That generates 8 rows here. The top half are going to be a series of T's, so 4 by 4, T, 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 F, 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 F. As we slide to the next vertical column, the rate of alternation just doubles and becomes T, T, F, F, T, T, F, F. And in this case, single alternation. After that, the truth values are filled in accordance with the rules. And in this case anyway, you know, to sort of skip to the end, as you see here under this main connective, there's a display which is all F's. And that's the case of having a logically false sentence. Okay, so next, I'm going to quickly stop the screen share for a moment. And I want to kind of show you guys next some stuff about how to use these truth tables to evaluate pairs of sentences to determine whether they're logically equivalent or not. All right. So yeah, let's try. I'm going to find one that's medium difficulty, not too bad. Okay, here we go. So what we do to analyze 2 sentences and then make a determination about whether they're logically equivalent or not. For the moment, I know Zoom is still open, but I like the screen that I have on my YouTube channel, so I'm going back to the YouTube, but you can keep the Zoom open if you like, and they're both running right now. Okay, so let us consider this little pair of sentences. Neither A nor B, and then both not A and not B. Okay? Now that's 2 sentences that are placed in this truth table. Actually, let me slide them over to the left a little bit so I have easier time reaching the book. So neither A nor B, and then over here, not A and also not B. Okay. So we create the cross as before, and just help me, let's see, I'm gonna pull up the other chat on this screen so that I see them both. 1 second, guys. Hmm. Okay, here we go. Yeah. Just getting my screens all set the way I want. Okay, thank you. So now I can see both chat streams in case you're chatting in either one. Tell me then over here to the left, this part shouldn't be that bad. What's written on the top left of this truth table? And now it's going to consider all the formula that are placed to the top right. So A, B, good. A, B. Now, how many rows will that require? We need to have a total of 4 rows. Good. To the left of, to the leftmost vertical column, it's A, and that's going to be, since there are 4 rows, the leftmost one is always top half T's, bottom half F's. So where there's 4 rows, that means 2 and 2. And as we go to the next successive column, it's TF, TF. Okay, so that's all done. Now we're just going to replace T's and F's in the order that you see here for each truth value assignment. If we go down vertically, we would see it this way. TTFF under every case of A, TFTF under every case of B. Okay. So let's see. Which one do you think we should do first in these 2 formula? By the way, what's the main connective of the 2? Let's get that on the table first before I go further. So hold that last question, new question. What's the main connective of this formula on the left? Where will I place the downward facing arrow relative to that expression on the left? The downward arrow should be placed above the tilde, that's right. Because the tilde occurs outside of the parentheses. And so that would be the last element of the formula to receive a truth value, because the tilde has to negate something, and it doesn't know what to negate until all that other stuff is filled in. So tilde. Now on the right side, what's the main connective on the right? On the other formula, which says, yes, it's the conjunction symbol, actually, Kalaya. It's the conjunction sign, because this is grouping the negation and of not A and the negation of not B. It's not simply the tilde, because there's no parentheses around the rest of it. Otherwise, it would be the tilde, but in this case, it is the caret symbol, or you may use the ampersand, okay? Now, we still have more work to do. So remember that in the 2 cases now we have 2 downward facing arrows because we're evaluating 2 different sentences, right? So we hold those arrows for last, but let's finish up this left side. So underneath the wedge, we're just looking at what's under A and what's under B to generate that truth value assignment. So with OR, with the OR sign, which is the little V, what's going to be placed here in the row 1? Tell me about row 1. It should say, because A and B on the left and right are both true, so in the disjunction sign, it's true, correct. Remember what you can about disjunctions. They're true all the time unless you see 2 F's, one on the left and one on the right. But these are both T's, so that's fine. Next case, TF. What's row 2, the truth value underneath the wedge? Row 2. Also true, correct, thank you. Because of the fact that the leftmost disjunct is true. You only need 1, basically. How about third row? Row 3, also true. This time because the right-hand side has the letter T, and it only takes 1 for the whole disjunction to be true. Finally, in the 4th column, row here, row 4 is where it is F, yes. Because the disjunction is false if both disjuncts are false. Now, let's finish this side by doing the tilde now. Now this tilde, we're going to have 4 letters, T's and F's, underneath tilde. Whatever letter it is going to depend on what's underneath the wedge. And it's just going to be the opposite of what's under the wedge, okay? So in this tilde column, what are the 4 values, starting from top to bottom? So just put them in the order, we'll go fast. What's the order of T's and F's? You have, FFTT, yeah, that's right. Well, no, sorry, not even. I just misspoke. So I see the correct answer now, and it's coming through. Not to worry, Jamie. It's FFFT. Why is that? Because it's reversing this part, see? TTTF, so the negation just flips it, FFFT. I probably shouldn't have done those little circles because it's going to make the board look a little messy. So I'm just going to try and erase them if I can, and then I'll redraw a bit. Okay, cool. So then over here on the other side, with concern to the conjunction symbol, we got to hold that for the last, and we got to do the tildes first on the left and right. So this tilde is not attached to the whole formula. It's just attached to the letter A. So what we're going to have in these 4 examples is what's the reverse of the letter here under A. So under this left tilde, just tell me 1, 2, 3, 4. What's the order of T's and F's there? In this column, you're telling me that it's F, F, T, T, and that's right. All right, good. But we're still a couple steps away. So we have to, again, save the conjunction for the end. The tilde still has to be done. Underneath this tilde, we're going to have 4 things. And it's going to be just the reverse of these 4 letters, which say TF, TF. So in that column, correct, guys, FT, FT. All right, so last but not least, under this conjunction sign, there will be 4 things in these blank spaces. And the value of the conjunction will depend on the value assigned to the left and the right tildes. So what's the rule of conjunction? With conjunctions, they're only true in one case, where both of the conjuncts are each true. So even one F is enough to throw off a conjunction from being true. One or both F is false, so only in one case where they're both true is it true. So now looking down here, first row 1, we have F and F. So that means that in row 1, what's the value? No, Tanya. It's F. Why have you said true? Maybe a typo, but think about it. It's conjunction. It's not biconditional. With a biconditional, 2 things FF make it true. With a regular conditional also, but keep the different symbols and connectives straight. This is the conjunction sign. And what I was saying is that it's only true in case both conjuncts are true. In this case, they are both false, so it's very much false. Row 2. Row 2. The value of the conjunction symbol in row 2 will say what? Based on this and this. F, yes. Why? Because of the left F. Because there is one F there, and that's not enough for it to be true. It have to both be T's. In the 3rd row, in this space, what is it, a T or an F? Correct, it is an F. Why? Because of this item on the right. T, F, they're not both true, so it's false. Row 4, the bottom row. Thank you, yes, it's true. This one's true because here we have T and T. Those 2 conjuncts are true, so the conjunction is true. Now, we circle these 2 columns that face down underneath those arrows, all right? And here's how we are now going to evaluate whether they're equivalent or not, okay? So when you've been given this task, when the problem asks you to take 2 formula, create a truth table, and then using the table, give me this answer. Are they equivalent or are they not equivalent? No, Brenda. Conjunctions are false all the time unless they are both true. Disjunctions are true all the time unless they are both false. Okay? So what you said in your question is not true of the conjunction, but it is true of the disjunction. Okay? With the conjunction, with and, with the caret or the ampersand, it's false all the time unless there's 2 T's. And if it's disjunction, it's true all the time unless there's 2 F's. So it sounds like you just got conjunction and disjunction mixed up a little bit. But just to remind you, if I say that I have an apple and a banana in my bag, that's only true if they're both there. If I say I have either an apple or a banana in my bag, that's true if I just have one. I don't need both for it to be an either or statement that is true. So conjunction requires both terms to be true. Disjunction just requires at least one. So anyway, when you finish the truth table, And the question is, are the two sentences equivalent or not? No problem, yeah. When you look at the finished truth table and you're judging are they equivalent or not, here's what you look at. In these two circled columns underneath the two main connectives, is the truth value the same in every horizontal row? And so my question for you is that question. Are these two sentences equivalent or are they non-equivalent? Do we have a pair of equivalent sentences or not? And good. You're telling me that they are equivalent, and that is correct. Why is it that they are equivalent? Because let's go line by line through the two columns. In the first row of the column, we have F's. In the second, F. In the third, F, and in the fourth, T. F, 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 T. That is the same downward order underneath both of those arrows. So they're equivalent statements. In other words, to say that not either A or B is logically the same thing as to say both not A and not B. So if you said like neither Trump or Biden had a good debate, that's the same thing as saying both Trump did not have a good debate and Biden did not have a good debate. I'm not saying I believe that, but just to make it salient with something that just happened recently. So there you go. That's a pair of equivalent statements, but they're not all equivalent. So let's try a different example. I'm going to quickly look at a case where they're non-equivalent. So let's see. 3.3 is this problem set which deals with equivalence and truth tables. So I'm looking at some of those questions in my own answer key here. Okay. All right, cool. So yeah, let's do this next one. This is just problem A of 3.3.1. Okay. 3.3.1. So now these are the two formulas to analyze with the truth table. It's basically not A and B. I'll do the ampersand just to change it up. And then the other formula is neither A nor B. Okay, so let's start by just asking this question. Where are the two main connectives at? Oh, Leonard, question. If they were to have the same amount of truths and false but in different order, no, Leo. They have to be in the same order. That's the whole thing. They have to occur in the same order. So it can't be like, oh, if you look at the whole thing, there's two T's and two F's in each one. If they're not the same in every case, then that's not equivalent. Because those cases that you look at horizontally are possible worlds. And so if there is a possible world where one is true and the other is false, that's shown by them not having the same letter in that horizontal row. They can't be equivalent if one could be true and one could be false. That's just the definition of non-equivalence. So it's not just about how many numerically there are in total of T's or F's. It's that in every possible world, these two statements have the same truth value. Okay, but good question. So two main connectives, and what are the two in this problem? What are the two main connectives displayed? The two tildes, right? Tilde here and tilde here. Now, on the top left, help me fill that part in. I just need to write the letters in alphabetic order, and this one's pretty straightforward, and it's just A, B. Okay, good. Once again, and I mean, I just want it to become like algorithmic, like almost automatic. Like, there's really almost no thought. It's just filling it in and mechanically. So how many rows does this need? It needs 4 rows. Underneath A, it's always the same, T, T, F, F. Underneath B, T, F, T, F. So I'll now go ahead and just fill in the assignment of each truth value in each row or column. In the first row, everything's true underneath T, A, and B. In the second row, A is true and B is false. In the third row, A is false and B is true. And then finally, in the fourth row, F is assigned to all the letters. All right, so again, as you guys know, we're going to save the tilde column for last because that's the main connective. It won't be able to be defined until we know what is here so that it can flip and reverse that. So underneath this and sign, you're looking at the two terms on the left and the right. So what's written in row 1 underneath that conjunction symbol? True, yes. And that's because both of them are true, and that's what a conjunction needs for it to be true specifically. Now, in the other three cases, can you tell me what's to be written in row 2, 3, and 4? It's F, F, and F, yes. Because in all those three other cases, there is at least one F on the left or the right, and that's enough to make it false. So that's all done. Now over here, disjunction. In the first row, underneath the disjunction symbol, we should have what, a T or an F there? A T, correct. And in row 2, someone tell me about row 2. Also true, because there's a left member, which is true. In the third row, what is row 3? And we'll just write row 3, colon. Leonard, I guess that's maybe what you're indicating with having those 3 shown. So yeah, in the third case, it's also true. What about row 4? Row 4 is the one and only case where a disjunction is false, because unlike conjunction, a disjunction is always true unless you see 2 F's. A conjunction is always false unless you see 2 T's. So this one is false. So we're not quite done. There's a couple more steps. This tilde sign, there are going to be 4 truth values underneath that tilde. And what they will be is the reverse of whatever is underneath the ampersand. So just maybe give me quickly the 4 cases in that order. Row 1, 2, 3, 4. What should I see in terms of T's and F's displayed downward vertically? F, T, T, T. Correct. All right. And that's the main connective, so we circled that because that's all done. Now we just have to finish this right-hand part. Underneath this tilde, we're going to have 4 truth values, and what they will show is the reverse of whatever is written underneath the wedge, the disjunction symbol. So what will that say? It will say F, 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 T. Correct. And why does it say F, 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 T? Because this says T, 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 F, and this is the opposite of that, as the negation requires. So now, question, are the 2 sentences logically equivalent, or are they not logically equivalent? Good, Lily. You've said that they're not equivalent. I have a little additional question to ask on top of that. Which row or rows display the non-equivalence in terms of numbered rows? Rows 2 and 3, yes, because in these 2 rows, they don't match. In row 1, they're both F. In row 4, they're both T. But in row 2 and 3, we will circle them horizontally to show this. They don't have matching truth values. This says T, this says F. So they don't have the same truth value in every truth value assignment in every possible world. Therefore, they are not equivalent. And let me see here. I'll just show you the information in the book that shows that. So this is on the Zoom. I'm switching over to it really briefly to give you this. This is problem A. So yeah, here you see it. And it's the same as we have here. Now they didn't circle the 2 columns. I've done that just to kind of make it even more visually clear what's being evaluated on the left and right. But you can see here, simply by circling horizontally this row, T is underneath the left tilde, F is underneath the right tilde, so they don't match. They only circled 1 because if there's even 1 row like that, that means they're not equivalent. But in this case, there's also the 3rd row as well, which they could have alternatively circled or circled them both. So when you have been given a problem which says, take these 2 sentences, use a truth table, and then fill the truth table in and tell me, are they equivalent or not, your complete answer would look like this. You'd have the 2 formula put in the table filled in, all the assignments of T's and F's provided, and then if they are equivalent, you'll just have these 2 rows circled going down, and they'll look the same, comparing them on the left and right in each horizontal ledger. If they're non-equivalent, then there will be 1 or more rows where the letters written under the main connective don't match. And in that case, you would circle that row or rows, and you would write that answer, not logically equivalent. If they are equivalent, you would write down the word logically equivalent, and then there's no horizontal row to circle, because there won't be any such case if they're in fact equivalent. Okay, so let me stop that screen sharing there. What we've basically done today is we've just gone over the homework problems, and we've also tried to go a little further with the truth table material. We've used these truth tables now to do 2 things. to either take individual sentences and analyze whether they're logically true, logically false, or indeterminate. And now we've also added to our knowledge how to use those tables to check whether two statements are equivalent or not. These are not equivalent. So to say that not both A and B is not exactly the same thing as saying that not either A nor B. And that's shown here in this table. So, I mean, that's my goal for today that we did manage to do. Don't forget that you have some upcoming homework problems that are going to be due on Monday. So, you know, if you need any help or have any questions about it, let me know. I'll be checking my emails every day until then. And I've always got my regular office hours, and I can always make appointments with students if they'd like to talk about anything. So let me know. All the first homeworks were graded a while back. And if there's any student that's still wondering what their score is, you could certainly ask me and I could tell you anytime, but you have to email me for that. So, all right, I guess then we'll be okay for today's meeting. Next time we'll go further and talk about how to use truth tables to judge whether statements are consistent. Okay, so logical consistency, we'll talk about that with the truth table method. And eventually we'll get to how to use truth tables to determine whether an argument is valid or invalid. Okay, so thanks everybody for all your help. I hope that you had a nice morning and a good afternoon so far, but till next time, take care and be in touch. And I guess I'll just see you guys then, okay? Bye-bye. So I'm ending the